Hey guys, it's Miss Davis. We are going to start our next unit today over basically nuclear radiation and nuclear chemistry. So this is kind of a fun topic, just because it can be very destructive, and so people kind of like that sometimes. So we're going to start with the basics today. Basically, just what nuclear radiation is, um, and then the types of nuclear radiation, and then we'll start getting more into it next time. So. Your Bellwright question for today is, what does nuclear radiation mean to you, and how have you heard it used before? So I want you to pause the video. I do want you to answer this and make sure you guys are doing more than just like one or two words. Like, you need to have a paragraph written down because this can be a pretty heavy topic. So pause the video, answer the question, and then come back to it, and hopefully you guys have a good discussion. For me, nuclear radiation, the first thing I think of when I hear nuclear radiation is like the after effect of an atomic bomb. That's why nuclear radiation can be so destructive. It's not just bombs, it's not just wiping out entire cities. It's a lot more than that. And actually, a lot of the stuff around us on a daily basis gives off nuclear radiation. And a big chunk of that is why they think that our cancer rates are going up, not just in the United States, but all over the world. And we'll actually talk more about that when we get to section 25.4. So, your essential question for today is, how do nuclear reactions differ from chemical reactions? Chemical reactions, we just basically got done with those. Those are our combination and decomp reactions and how those take place versus how do these nuclear reactions take place. So by looking at that and comparing and contrasting, we can see how they're different from each other, but they are also similar at the same time. Hold on, I gotta grab a crying baby. Come here, Davis. Come here.
Oh, you want me?
You wanna come say hi? Yeah. Okay, let's say hi. Okay, I know. All right. So, radioactivity, what this is, it is basically, it's spontaneous emission of rays or particles from certain elements. And so what that means is it just kind of breaks down. It's spontaneous. If you're spontaneous, you're kind of crazy and random. That is exactly what radioactivity is. It's very just random, based on the type of atom and it's based on the type of element that you have. So if you have an element that is spontaneous, then we refer to that as radioactive. Okay. And then nuclear radiation, the actual the actual being of nuclear radiation, that's what the elements will disperse and what they'll get rid of. So they'll get rid of rays and particles. The rays are kind of an accumulation of the particles, mostly in the form of alpha, beta, and gamma rays, which have to do with how they break apart the nucleus. Okay, so and then a big part of why we understand radioactivity and nuclear radiation because it came from Madame Marie Curie. So you've probably heard of her before, but she paved the way really with nuclear radiation, which was kind of unheard of at the time because she was a woman, and in the early 1900s, women didn't get to contribute much to science, but luckily. For us, her husband was also a physicist, and he let her help him in the lab, and then we developed a lot of understanding because of her. So, Marie Curie, her husband, and then another colleague of theirs, they won the 1903 Nobel Peace Prize because of their work with radioactivity and nuclear radiation. She was born in Warsaw, Poland, and you guys will actually watch a kind of a short documentary on her either today or toward the end of class or the beginning of next class. But her entire family was basically teachers, and so they were always very receptive of her wanting to find out more and questioning things. So again, early 1900s, late 1800s, this was unheard of for women. They were to stay in the house. They were supposed to do housework and take care of the men and their families. And so she kind of wasn't about that. So, Marie Curie actually died in 1934 from aplastic anemia. What that is the body can't develop new red blood cells, so all of her blood cells were dying and she couldn't make new blood cells. That can be a big cause of working with that nuclear radiation. So her work actually ended up killing her. And then to this day, she has a lab, I believe in Poland, and they can't touch her notebooks or her like papers because they've been penetrated so much with nuclear radiation that it still gives off too much of those damaging gamma rays. And so if anybody were to go in there and touch them, they could actually be exposed to that, and then you can develop really bad health problems like aplastic anemia or cancer. You can have liver failure, all sorts of not really good stuff. So we still can't really touch her notebooks very much unless you are suited up in a hazmat suit designed specifically to deal with nuclear radiation. So continuing on with nuclear radiation, to kind of compare the types of reactions, nuclear and chemical, the atoms do become more stable in both. Okay. And so if it's stable, that means they're not likely to change. Hey, you're okay. You're okay. So the difference though is nuclear reactions, they are going to start with something that's unstable, and then they're going to break apart the nucleus. Okay, we know that with chemical reactions, they don't break apart the nucleus. They just kind of either join or split apart the atoms as a whole. Nuclear reactions will split apart the nucleus, hence the term nuclear, okay? And then because of this, because the nucleus has all of that energy in it, if they're splitting that, it's going to give off a large amount of energy. So you can have explosions, or actually what like Marie Curie came up with is you would see little flashes of light. But these flashes of light are coming from something that is, one millionth the size of the end of a needle. So you can see these little flashes of lights from something that small, so it must be a lot of energy. Now, some things that differ between nuclear reactions and chemical reactions are that nuclear reactions won't be affected by changes in temperature, pressure, or catalysts. We know that chemical reactions will. And then finally, nuclear reactions, they can't be slowed down, they can't be sped up, and they can't be stopped. So once they start, you're in it until completion. So I want you to take that information now that we just talked about on the last slide, and I want you to tell me, why is it that nuclear warfare is taken so seriously? So pause the video for a second, and I'm going to pause and take care of a baby, and we'll be right back. Alright, so hopefully you guys came up with a few ideas as to why nuclear warfare is taken so seriously. The biggest thing is, again, once you start, you can't stop it. It's not like something that you drop some sort of nuclear weapon on an area and then you're like, oh, just kidding, I changed my mind. Like, once you start, you got to go until completion. And so once all that nuclear radiation starts getting emitted, there's no stopping it. There's nothing that you can spray. There's nothing that, there's no like medicine that you can take that'll stop it from working its way through your body. So once it starts, you just kind of you're at its mercy until all of the atoms involved are going to be stable again. So, and then the other thing is it emits a lot of energy. So we've seen, and we'll actually do some research with this, that after Hiroshima and Nagasaki, the huge amounts of energy that took place. Sorry, I lost my train of thought with my child here. The huge amounts of energy were in and of itself really bad. Okay, so we're going to continue on here. So we have three types of nuclear radiation. The first type is going to be alpha radiation and alpha particles. Child. So alpha particles, these are going to be made of 2 protons and 2 neutrons, and so they don't have an electric charge. So if you have this unstable nucleus, kind of like uranium-238 here, it will go through alpha radiation or alpha, it'll lose an alpha particle. So alpha particles basically look like a helium particle. Okay. So you will decrease your atomic number by 2 because it's losing those 2 protons, but it's also losing those 2 neutrons. So your total amount of mass that you're losing is going to be 4. Okay. I know I have up here 2, but it should be total of 4. And then these aren't super bad for us because they are huge and they're heavy. So they can't work up a lot of momentum. We can actually stop these with our skin or clothing or piece of paper, what have you. But if you ingest or you take in something that's emitting alpha particles, because your internal organs are made of these soft tissues and they don't have to travel very far to penetrate the soft tissue, that can lead to a lot of health issues. Okay. So, and again, down here we've got uranium-238. It goes through something that causes it to become unstable. It emits an alpha particle up here. Okay, so this is kind of like a helium particle. And then what you're left over with is what we call the daughter nucleus, and this is thallium-234. So you see that the mass number changed by 4, and then the atomic number actually changed by 2. Okay, so you will have to change the atom that you're working with when you go under nuclear radiation, and you guys will actually get a worksheet on that probably next time. Okay. Now the next type of radiation is going to be beta radiation. We're going to split apart a neutron in an atom, and what it does when you split a neutron is it splits into a proton and an electron. Okay, the proton actually stays in the nucleus, but the electron gets released. And if you're losing that electron, you're going to get a positively charged atom. So if the radioisotope undergoes beta radiation, the mass number stays the same, which we'll see here with thallium-234. Okay, so its mass number is 234, its atomic number is 90. And so your mass number will stay the same, but your atomic number will increase by 1. So then we get our new element here. And then we have an emitted beta particle. Now beta particles, they're a little bit smaller and they're not as heavy. So they're going to be more penetrating than alpha particles. These can be stopped with like aluminum foil. Okay, so you know old movies and the aliens are coming or whatever, and they put the aluminum foil on their head. That is because of the beta radiation. So finally, the most penetrating and the most harmful types of radiation is going to be gamma radiation. This is a very, very, very high energy photon. And remember, photons are actually smaller than protons. The photons actually make up the protons. And this is kind of like a byproduct. So when you have alpha and beta particles occurring, the gamma rays actually come as like a byproduct of that because of the splitting of the nucleus. So gamma rays, they have no mass, they have no charge, but because of that, they are so dangerous. They can be stopped by basically lead or like several feet of concrete. So gamma rays actually don't really change anything else of the atom because it's that byproduct, but because it's so small, it's very, very, very dangerous. Okay, so here's just another picture kind of showing that. So our alpha particles, these can be stopped by your hand, not a big deal. Beta particles will go through you, but they can be stopped by something small like aluminum. And then gamma rays, these can be stopped by lead, but it still has to be several centimeters of lead. It just can't be a super thin sheet. Okay, so I have about 50 seconds left until my thing runs out of time. So I want you to do this think, ink, pair, share. What property of electromagnetic radiation determines the penetrating power? And then I want you to think about a time when you would be exposed to gamma rays and what did you do to protect yourself. So think about the dentist or the doctor. I will put the answers in the notes of the little notes portion of the PowerPoints so you can kind of check your own answers. But talk to each other, discuss, see what you can come up with. And then finally, here is your homework for this unit. One thing I do want to make sure you guys are aware of, you have stuff to be working on like every single day. I am taking time from my son to give you stuff. You need to work on it. If not, it'll come back to bite you when I come back in 4 weeks. Okay? Thanks, guys.